This is the demo video for our proposed hook for the UniswapV4 hackathon. We try to provide a combined solution to hedging permanent loss and lever via dynamic fees and hedges to achieve both delta and gamma neutrality. When providing liquidity to Uniswap, LPs are subject to the price mechanics of the constant function formula. This is x times y equals k. Due to LP's position having negative convexity, which can be proven using Jensen's inequality, the value of the position will always be inferior to simply holding the tokens, without, of course, accounting for fees. There are two main methods of quantifying these losses, which are loss versus holding, or impermanent or divergence loss, and loss versus rebalancing, also known as lever. While impermanent loss has been the primary metric for quantifying LP losses on Uniswap, it has some major drawbacks. It compares LP value to the value of simply holding the tokens, which is an unrealistic strategy. Furthermore, if the price diverges and then returns to the original price, the impermanent loss is zero, completely disregarding volatility. Lever, on the other hand, is path dependent. It takes into account rebalancing and arbitrage opportunities given a time series of prices. It occurs mainly due to AMMs having stale prices. Moreover, it has been proven that LPs have underpriced volatility and therefore market risk, foregoing additional profits and having a negative volatility risk premium. This can be demonstrated by deriving implied volatility from Uniswap position and comparing it to realized volatility extracted from any liquid market where price discovery is supposed to occur, such as Deribit. So, given that an LP has already chosen a pool, there are two main methods of reducing these losses: using hedges and dynamically modifying the pool fees. Due to the negative convexity of LP value function, their positions cannot be hedged solely with a delta 1 or linear products. However, for small enough price movements, a delta hedge can be sufficient to offset lever. This can be achieved either via selling futures or via on-chain borrowing and setting a rebalance threshold from which, if surpassed, a rehedge is executed. For LPs that desire a complete hedge to offset all directional risk, products like power perpetuals or options are the preferred approach. We implement a basic proof of concept of how LP Greeks are updated and how these can be used to compute any hedging updates and verify that the position is correctly hedged. On dynamic fees, to correctly remunerate LPs and price volatility accordingly, as well as reduce price impact for large swaps and account for market conditions via gas prices, a dynamic fee system has been implemented. To achieve this, we extract the implied volatility of the pool from the volatile asset drift and return from the pool fees, using the formula derived by Daniel Alcaraz. And with that, we attempt to devise a simple model that dynamically readjusts the fees with a discount factor based on volatility risk premium and the aforementioned parameters. This is because whenever implied volatility is higher than historical or expected volatility, providing liquidity yields a positive expected return. However, if the implied volatility is lower than historical or expected volatility, the returns become negative. We are also currently investigating the implied volatility formula proposed by Guillaume Lambert, and there is significant room for improvement in both the parameters and the formulas used. These are preliminary implementations to have the proof of concept ready for the hackathon, but will likely change in the following weeks. We will also be performing a backtest, taking of course care of the backtesting overfitting, as well as a forward test of the models, along with some unit integration, fast tests, and formal verification of the code. So how does it work? Well, first we need to compute implied and realized volatility, and this can be done via Chainlink and Brevis. Then we adjust the dynamic fees to minimize lever. In the after swap, we compute the new LP Greeks after the price movement and we hedge them accordingly. On the right, it can be seen the basic derivation of the value for an LP position in UniswapV3, delta, gamma, and the function that represents the loss given a price movement and a certain range. The main idea of the model was to adjust the dynamic fees based on the difference between realized and implied volatility and try to move towards a risk-neutral DeFi. So whenever implied volatility is higher than historical, as there is an expected return for LPs, we will reduce these fees, benefiting traders. And when it's the other case around, we will increase fees, therefore benefiting LPs and pricing volatility accordingly. These are two simple functions that we just came up with, but are subject to study and modifications. On the left, it can be seen the formula devised by Daniel Alcaraz to get the implied volatility from a pool, given the return from that pool in fees, the drift of the asset, and some time that we will assume it will be 1 in years, and then we can convert volatility to whatever period we want. And on the right is the formula that we propose as a discount factor for volatility. However, this can be further simplified, and it just comes from this simple idea and multiplying the two functions, taking into account both cases and how they interact with each other. Then this is a real example provided two geometric variant motions for volatilities, and these series actually look very similar to what one can observe in reality, and then how the discount factor evolves. Then this is a basic representation of the architecture that we biased and how we are using each provider to help us either get the data that we need or hedge accordingly. So what are the next steps? In the following weeks, we will complete the hedge manager contract to correctly handle all re-hedges. And then for the delta hedges, given some threshold that will be optimally computed from current market conditions, we will track the real cost. And then for delta gamma hedges, we will add the corresponding connectivity with external protocols. Then we also need to adjust the model parameters and do some forward testing with a hook with real market data. We will study the real volatility risk premium effect on fees and change the functions accordingly. And probably we will create a backend to abstract the computation from the blockchain, as they can be very gas intensive. We will also design a small frontend to allow LPs to utilize the hook. So this is our team: Carlos, Sergio, and me. Carlos is the head of cybersecurity, Sergio was the blockchain engineer, and I did the quantitative research. Although we have all been involved in every part of the process. Here is a link to the repo. And thank you very much for your attention. We hope that this hook turns to be useful for LPs and serves as an inspiration for future ones.